Okay, so let's get started. Small class today. Lab is due, data science symposium is running today, but that's okay. I think I'm glad that all of you made the time to come. So what we will do today is actually continue the discussion on distributed file systems that we started last time, but then go well beyond NFS. Okay, we are going to actually look at 4 different file systems today. Okay, we'll talk about Coda, we'll talk about xFS, talk about HDFS, we'll talk about Google file system briefly. Okay. You have a question?
Can I start us off with 2 questions about the third lab? Actually, just 1 question about the third lab.
Okay, we can take a pause and talk about the lab and then move on to the lecture.
Sure. So I'm confused what the third experiment wants us to actually, I'm sorry, the second experiment wants us to actually evaluate for time.
Okay, I don't remember the write-up. What does the second experiment entail?
So basically, we need to create an experiment that shows that you can validate the cache or maintain cache consistency. And it's specifically asking, what's the overhead of cache consistency operations? What is the latency of a subsequent request that sees a cache miss?
Yes.
I was wondering if you could provide some more detail on how to do that.
Okay, so I think what it is asking you to do, first of all, I think there's one experiment clearly asks you to evaluate the benefit of caching. Did you see an improvement over not having a cache at all, right? Then the second, I think, experiment, if I remember what you're asking is, because you implemented a cache, now you have to have a cache consistency layer that is ensuring that whatever data is in the cache is accurate, right? And that's extra overhead that you, code you write, extra overhead that it imposes. So all that you need to do is to evaluate the overhead either in terms of latency of sending an invalidate or an update, depends on what you've done. You could send invalidates, you could send updates, any of these messages that have to go to the cache. Okay? So any operation that you consider to be required for ensuring cache consistency, evaluate the overhead in terms of latency or number of message exchange, which is just counting, that's not even measurement.
Should we be measuring the latency of the function calls to the cache? Like get,
Yes,
put,
absolutely.
pass?
Yes.
Okay,
Yes.
those are going to be very small.
Yes,
Values.
that's okay.
Okay.
That's fine. I mean, it's just asking you to think about what cache consistency means, right? And then the other part was after you invalidated, if that object gets accessed again, it's a cache miss because it has to be fetched from the source. That's assuming you are sent notifications for invalidates as opposed to updates. If you sent an update, then there is no subsequent cache miss actually, because it's going to be hit. But assuming you sent an invalidate, it's a cache miss. So it's just asking you to compare cache miss versus hits.
Got it.
Right? So that's all there is to it.
Sounds good to me.
Okay, it's not very complicated, but you just need to understand what is being asked. Okay, so we do have office hours after class if there are more questions, but let me start with distributed file systems. The first one we are going to talk today is called Coda. Okay, it was a distributed file system that was developed in, I think, about 2 or 3 decades ago. It started as a research project at Carnegie Mellon University. And the main goal of this file system, unlike NFS, which you saw last time, right, that was really a client-server file system. The main goal of Coda was to support mobile clients, mobile devices. Okay? Their vision back then, which was still early days for having lots of mobile devices, was that there would be a day where users would carry lots of mobile devices that would be their primary device for data access, and these devices would be very different from, say, a desktop client which is on a wired internet. Okay, these would be wireless or mobile clients. They would frequently disconnect from the network. Okay? You think about how your laptop operates. Okay, you may be in an environment where there is Wi-Fi access, so there's network coverage, and hence you can connect to your file server. Okay, so you're connected. Then you go somewhere. You take a car ride or you may go on a plane somewhere. In that, during that transition, you may not be connected to the network. Okay, so you disconnect. Okay. Specifically, if you are on a plane and let's say that you don't have any Wi-Fi or anything like that on the plane, you may be working on things on your laptop, but you're disconnected from the server. And then eventually you go into an environment where you reconnect and then you have access to the server again. Okay, such environments are called weakly connected environment, which essentially means that the client will be connected to the network for some periods of time and may be disconnected for other periods of time. So how do you design a file system that is specifically designed for such environment? Okay, that's essentially the design goal of the Coda file system. Okay, so then you could say, what could you do? Okay, suppose that you have a user. Okay, they have kept all of their files on a file server. Okay, so they use their laptop to access the files on the file server. Then they basically disconnect from the network. Okay, what would be the good experience to provide to the end user? Yes.
Maybe cache the file on the device and update it later when you reconnect.
Okay, cache the file. So the thing you got to remember is the default when you disconnect is that your files become unavailable, right? So you could throw an error saying your files are no longer accessible. Too bad, right? That would not be a pleasant experience for the user. Okay, what would be nice is if this disconnection was as transparent as possible. You don't actually even show that to the user. Okay, so if you had proactively cached files that the user is accessing and keep a local copy before this disconnection happened, the network gets disconnected, there's a copy of the file, you continue to work on the file as if nothing has happened. Okay? And at a later time you reconnect, then you can resynchronize the changes. Okay? You can actually see some of these ideas now in many other systems. So if you use email systems like Gmail, for example, right, web-based, browser-based, okay, that typically only works if you are connected. But Gmail has now introduced an offline mode where it transparently caches some of your email in a web browser cache. So even if you're disconnected, your browser can still access your email. Okay? So these kinds of scenarios allow you to give better user experience to your clients. So this is exactly what Coda would do for us. Okay? So Coda, like any file system, distributed file system, has a set of servers. Okay, you will see that there are file servers shown in this picture. Okay, typically you have you can replicate your files across servers. Your files will have a file handle which will indicate what server it's stored on and the file handle. Okay, that's no different from any other file system. So we won't go into the details there. But what is more important for us is how it deals with network partition, how it keeps things transparent for the user, and so on and so forth. Okay, so it can deal with disconnections at different layers. Okay? So this figure is actually showing us disconnections where there's a network partition, so even the servers of the file system get disconnected. In the next slide, we are going to see what happens when a client disconnects from the server. Okay, so let's take this example where there's a client A, okay, in the Coda file system, and there's a client B, as you see there. Okay. The files are now distributed across 3 different servers, S1, S2, S3. Okay, for simplicity, let's assume they're replicated. Every file is on all of those servers for performance reasons. So client can go to the nearest server and get the file that they want. Okay. So now let's say the network actually gets partitioned. It gets broken into 2. So this client A can still access S1 and S2. Okay, so it is still able to access some servers, and client B can still access server S3. Okay. So from a client's perspective, all of this is still transparent because there are still some subset of the servers accessible to them. Okay. Now clients might continue to read and write files to those servers. Okay. Now if you read or write files to on the left half, the servers S3 on the right half will not see those writes because the network is presently disconnected. Well, not disconnected, partitioned. Right? So what Coda in this case is going to do is it's going to track which files have changed, and it uses what's called a version vector. Okay? So you can assume that every time you update a file, you increment the version number of that file. Okay? So the version number tells you what is the latest version of that file. Okay? In specifically what Coda does is it maintains a version vector as opposed to a single version for a file, and then you have one element of the vector for each server. Okay? So if your version vector says 111, That means that the file is currently at version 1 and all 3 servers actually have version 1 of the file. Okay. Now, when this gets disconnected, let's say you update some file, so the version will get incremented on S1 and S2. So, the version vectors that are maintained by those 2 servers will essentially become 2 to 1 because they see the update, but S3 has not seen that update. Okay. Let's, for sake of making this example interesting, assume that the same file was updated by client B as well. Okay. So, that update only goes through S3. Okay. So, you open the same file on 2 different clients and you updated it. So, in this case S3 is going to update the version vector. So, its version vector will look 112 because it has updated the same file and it will increment its version to 2, but it has not been able to send those changes to S1 and S3. Right. So, now when the network partition is healed, the network reconnects, you are going to actually look at every file in your system and compare the version vectors. Okay. And here you are going to see a write-write conflict because you see that the file was updated on S1 and S3 by client A and the same file was updated on the other machine by client B. Okay. So, you will flag this write-write conflict. Okay. Now, the system does not know which version of the file to pick. This is no different from conflicts that you see in source code control. Okay. When if you use Git or SVN, if 2 users actually change the same file or change the same line of the source code and push it, you are going to get a conflict. Okay. Same idea. Okay. So, now in this case you are also going to throw an exception to the user saying there is the same update to the same file, you can figure out how to reconcile this write-write conflict. Okay. Just as if you have a version control conflict in Git or SVN, you ask the user or the programmer to resolve the conflict. The same is true here. Okay. But the important part is that it can actually detect that by keeping version numbers and so on. Okay. So, that is how you will deal with this when the network gets partitioned, but some servers are accessible to clients. Okay. The more interesting problem is when you have a laptop and you disconnect the laptop from the rest of the network. Maybe you take a plane ride. Okay. And then you now want all your files to be accessible. This is where Coda actually makes things very interesting because it has a very aggressive form of prefetching and local caching. Okay. And this is called hoarding in case of Coda. Okay. So, you essentially keep a hoard of your files locally. All of this is done automatically for you. Okay. The system is going to figure out what files do you access typically and keep a local copy. Okay. It is automatically going to do this. So, when you are connected, you are essentially in hoarding mode where it is trying to figure out based on your access pattern what files you typically access and keep a hoard. Now, maybe at some point you will disconnect, you may go somewhere where there is no Wi-Fi or you may take a plane ride or something. At that point your system goes into emulation mode. Okay. So, what emulation mode is, your client, the Coda client is going to pretend as if you are connected. It is not even going to tell you are disconnected. Right. So, you will see a copy of all of your files. So, your entire file system structure looks like it is present on your local machine, even though only a subset of the files are present. So, if you continue to access the same files that you always do and there is a local copy, you do not see any problem at all. Okay. The only time you are going to see a problem is if you try to access a file foo that you had not accessed before and for some reason the system did not know that you are or did not predict you are going to access it, and then you see an error saying this file is actually not present. But by and large, if you continue to access similar files, you will not see any problem. You will be in emulation mode. All the files are still available. You can open them in a browser. You can make edits and you can save them and so on. All of those changes are saved locally and tracked. Okay. Now, eventually, you might actually reconnect to the network. At that point, your client will resynchronize with the server. Okay. It will essentially upload all of your edits to the server, to all the files, and download all the changes that some other client may have made to those files and rehoard those. So, you will see that in this case you are in reintegration mode where you are resynchronizing. You are doing pairwise synchronization, saying here are the changes that the client made and send me all the changes that the server made. So, you integrate that. Here also you can find a write-write conflict, just as we saw in the previous case. The same file was modified by a user in disconnected mode and somebody else modified that file and uploaded to the server. The version vectors won't match and you will know that the file was modified by 2 users, and you will basically throw a conflict to the user saying this file cannot be integrated without manual reconciliation. Okay, so this is essentially called manual reconciliation. So you will essentially, and of course, while you are integrating, you may disconnect again, because you may not have enough time to have uploaded all the changes. You may disconnect, you may go back into emulation, so you will see that there's a loop there. However, if you stay connected for a long enough period, you might upload all the changes and go back to hoarding mode. So you will essentially cycle through this state transition diagram, and your client will always look like it's always connected. Whether it's actually connected or not, you will not see. Your applications won't see. Okay? Is this clear? Because there are many mail clients that do that also. Okay, if you take standard Apple mail client, it keeps a copy of most of your frequently accessed mail folders locally. So if you are connected or not, all your mail is cached locally, and then it will keep resynchronizing with the server if you make any local changes while you are disconnected. So many other applications now use similar ideas, but they originated back in the days of Coda, okay, when this file system was introduced. Any questions on this? Okay, so few other things I want to mention, because you want to have clients that disconnect, reconnect, and resynchronize. One of the nice things that Coda did was it basically said in what order should we apply changes and so on. Let's use ideas from databases. Okay, just as you had concurrency control, where multiple queries could run on the database, and the database state is as if those queries ran sequentially even though they ran in parallel. Okay? This was called serialization in the context of database. Here also you have different clients making changes to files, and when you are trying to resynchronize files or reintegrate the changes to the server, what you get is essentially serializable semantics, which is transaction semantics, which say that these changes will be applied as if they were done sequentially, even though the users may have edited them in parallel and so on. If you can't do it, if there's a write-write conflict, you will throw an error. But if there's no write-write conflict, it will look like they were serialized in some way, even though they happened concurrently. So another nice thing here is it use some ideas from databases and use them in the context of file system. Most file systems are not going to give you transactional semantics or serializability. But because here your disconnected operation, you want to reason about some consistency. Because if you reintegrate changes, does this make any sense? They said, let's assume that the semantics are serialization. Okay, so that's another thing that you want to keep in mind. Okay, so I won't go into the caching because there's not a whole lot interesting thing to say there. But with that very brief introduction to Coda, I'm going to switch gears and spend a little more time talking about another file system which is more interesting and has lots of other interesting features. It is called xFS. Okay? Small x, which basically it's like a cross, and that essentially, that x essentially means no server. Okay? So it's called a serverless file system. Okay? Think of it almost like a peer-to-peer, although that's the wrong term here. It's not really a P2P file system, but essentially in typical distributed file system, there's a file server and there's a file client. So it's a client-server architecture. In xFS, there is no server. All data can be stored on any machines. Okay, so all machines are equal. Every machine can act as a client of files, or it can also store some data and act as servers of files. Okay, so you're essentially using disks on multiple machines so that you can use the storage space on lots of clients, and there are no distinguished machines called servers. You can essentially keep anything anywhere. Okay, so that was the philosophy really, that it said anything could be stored anywhere. It was a research file system, but there are lots of interesting things here. Okay, so I'm going to talk about 2 or 3 different key features of xFS. Okay, namely the use of striping, the use of RAID-like storage, the use of log-structured file system. Okay, these 3 concepts actually arose in many different storage systems or early file systems. xFS put it all together in the context of a single file system. But in order to understand how xFS did it, I need to first explain what is striping. We'll look at what is RAID. We'll see network RAID, and we'll look at log-structured file system. Okay? And then we'll put it together. So let me start with the concept of what does striping mean. Okay, I'm going to have to draw a picture here to explain that. Okay? So let's assume that there's a file server that has 3 disks. Okay, so you think of a machine that has 3 separate disks, okay, and you want to use this disk to store files. Okay. Typically, you would create a separate drive or a volume on each of those disks, and when you store a file, you have to decide which volume you want to store it in. So each disk acts as if it's a separate storage system. Okay. So this architecture is also called in industry, it's called JBOD architecture, just a bunch of disks. I don't know who came up with that name, but it's called a JBOD architecture, okay, which means that each disk is independent, okay, and you are going to essentially store your files based on which disk or which directory you want to store it in. Okay. So now the file server is making use of all the storage space on all the disks depending on where the users choose to store it. However, there are lots of issues with this architecture. For example, if you start storing more data on, let's say, your E drive, which is mapped to that disk, that drive might fill up and the other drives might still have space and you may not be able to store any more data, right? Or you might have certain files that are stored on a certain disk that are very popular. So that disk has a much heavier load than other disks. So there is load imbalances in the system depending on which files are popular, which files are not. When you create a file, you do not know what kind of popularity or access pattern it's going to see. So you just store it where you as a user think is the best directory for it. But if it so happens that that's an overloaded disk, your files will see worse performance than other disks. Okay? So there are all these issues. The storage space gets utilized in a skewed fashion, the loads may be skewed and so on and so forth. Okay? So to address this problem, researchers came up with the idea of striping. Okay? And the way striping works is as follows. Okay? In a normal case, if you actually have a file, the entire file is stored onto a single disk. Okay? So you create a file, you store it on C drive. Okay? That goes onto that disk that C drive is stored on. Or if you put a D drive as a different disk, it will go there. Okay? In striping, what happens is you take a file and you are going to partition it into smaller chunks, which we are going to call blocks. Okay? And you are going to essentially store different blocks on different disks. So block 1 will be stored on disk 1, block 2 will be stored on disk 2, block 3 on disk 3 in a round robin fashion. Okay? So you take a large file, you chop it up into smaller blocks or chunks, and then you essentially round robin store those chunks. You will store essentially block I will be stored on disk I mod n, where n is the number of disks. Is that clear? Okay. So every file is now going to be stored on all disks. You are going to essentially chop it up into little small pieces and store those pieces and scatter them across all the disks in your system. Okay. Now, this is essentially called striping a file. So essentially now your file system looks like a single logical disk that's a union of all those disks. Okay, so you are now a logical disk abstraction where your disk is essentially a larger your logical disk that's equal to the sum of the storage space on all the individual disks. Okay, so what does this give us? Why would we do such a thing? As opposed to our old architecture where each disk is treated independently, users do whatever they want on each separate disk. You see an advantage of doing this, or disadvantage perhaps, yes?
If one of the disks goes down, at least you have a file on the other 2 disks or parts of it.
Okay, that's a disadvantage. So we'll come to just failures, but in just a bunch of disk architecture, if disk 2 fails, all the files that were stored on disk 2 are gone. Okay? Maybe you got to go to backups and recover it, but all the files that are stored on disks 1 and 3 are still accessible. Okay? In this case, because every file is stored on all the disks, not that a file is replicated. You are basically taking maybe a first 1 kilobyte of the file storing here, next kilobyte of the file storing here, and so on. If a disk fails, portions of every file are gone. Right? So every file is now impacted. So from a failure standpoint, actually striping is worse than just storing it on a bunch of disks. Okay, yes?
It's kind of like implicit load balancing.
Okay, it is implicit load balancing because, so the good part about it is now there are no loads because every file is stored on all the disks. If some files are popular, you will access them, but those IOs will be spread across all the disks because you are going to retrieve a large file and you will take some parts from here, some from here, some from here. So the high load for that file is now spread across all the disks. So you are getting load balancing. Okay, yes.
This disadvantage, I think isn't that depends on what kind of file you store. If you have a video file, then if you lost just like a fourth of the file, the video, you probably can still like drop the image.
Right. So you are asking about what to do with failures. We'll come back to failures in just one moment. Okay, failures are clearly a problem here, but the advantage is you got better load balancing. Yes.
How do you actually keep the metadata where you store every chunk of the data?
Okay, that's a good question. Question is how do you decide where you are going to store the file? So every file is now still going to have an inode structure. I remember I introduced that last time, where essentially for every file you have an index, where the index is going to point to the disk block. Okay, in this case your index is going to say it's on disk I block J. So block 1 is on disk I block J, block 2 is on disk I prime J prime, and so on. Okay, so you are going to keep some metadata which is going to tell you that the ith block is essentially on disk number X, block number Y on that disk. So it is just a straightforward extension. So that's not a problem really, right? Yes. Okay, so question is about security. It's not going to give you better security per se, because you're just chopping a file into smaller pieces, right? So you think of a text file, you put the first 5 lines here, the next 5 lines here, next 5 lines here, and so on. Right. So we have not talked about encryption here, but we'll come to security next week. Okay, so this is just standard file system. Yes. Jim.
So in terms of load balance, it's not only the size on each disk, but also you can speed up read and write.
Yes. Okay. So that's the other advantage, which is not just that the load is balanced, but now you actually have parallelism. Big advantage, right? So you want to access the file. Okay, you basically now send the request in parallel to 3 disks. So you are essentially getting 3 times the throughput than if you had stored on a single disk. Very similar to if you have multiple cores and threads that run on multiple cores, you get parallelism. You are actually going to get parallelism. If you have 100 disks, you essentially stripe the file across 100 disks and you try to read it all at once, you are going to get higher throughput. Okay? Better load balancing, higher throughput. Of course, you are using the storage space better. So these are all advantages of striping. So large storage systems will all employ some form of striping. Okay? So this is the concept of striping. Now, there's clearly a problem with this approach, which was already mentioned. That's the problem of failures. What happens if a disk goes down? Okay? Then you basically lost some part of every file in your system. You cannot get it back. Okay? It's not like only files that were stored on a certain disk or every file gets impacted. So we got to deal with that problem now. Okay? That is going to bring us to the second concept. So it covered striping. Second concept is redundant array of inexpensive disks or independent disks, which is called RAID. Okay? So that's an acronym which is redundant array of independent disks. And the reason you have to do this is this failure thing is not a hypothetical problem. Okay? If you assume that a disk fails with some probability, as the number of disks in the system keeps increasing, the probability that some disk fails, even if they're independent failures, start approaching 1. Okay? The more the components in your system, even with independent failure, the probability of failures is 1 minus p to the power n. Okay? So here's a simple example where typical lifetime of a disk is 50,000 hours. Okay? That's around 6 years. If you have a 670 disk system, because of independent failure, the mean time to fail in the system is down to 700 hours, okay, which is barely 1 month. So every month you are going to see a failure in your system. Okay, that's basically just probability how things work. Okay, so and the more the number of components, the more likely that some component is going to fail very quickly. Okay? So that essentially means that if you assume striping and you have a large number of disks in the array, you construct a 100 array system, you are going to see failures very quickly. So that means that you better design your system to handle these failures upfront, because you don't want downtime when the failure occurs. Your question, Justin?
It's somewhat unrelated. I'm just wondering, from a hardware perspective, why are these disks actually failing?
Okay, question is why do disks fail? Disks fail for, well, these are magnetic disks. Remember now there are solid state disks. So magnetic disks have moving parts. right? So they are like CDs with platters that spin. Okay, so they might fail for any number of reasons. The motor fails, right? The motor basically fails, so the platter won't spin, or when the platter is spinning, if there's a shock to the system, then the disk head goes and scratches the surface, and then some data gets corrupted. So there are all sorts of problems. In fact, there are papers that actually show why disks. Actually, paper they looked at lots of disks in a data center and articulated causes of disk failures. Everything from mechanical failures to bad magnetic recording to all sorts of other problems.
Gotcha.
Right? So disks will now solid state disks don't have any moving parts, but they will also fail because their lifetimes are actually not even as good as magnetic disks. We are getting better. Yes.
Predicting this properly, but why is it that as the number of disks increase, then the chances, the probability of failure keeps increasing? I would say that if you have a lot of disks, then it means it would be the other way around.
No, it is basically simple probability, right? If P is the probability of failure, right? So 1 minus P is the probability that there is no failure in the system. Then there is 1 minus P to the power n is the probability that no disks have failed at all, right? So you do 1 minus this is the probability that some disk is going to fail. And as n is going to approach infinity, that number is going to start approaching 1, okay, because of independent disk failure. So it's very simple probabilistic argument, not like every disk is reliable, so even if I buy 100 disks, they will all be reliable. That doesn't quite work because things do fail independently. Everything is probabilistic, right? Okay. All right, so now let's see what we can do about this problem, because hopefully you are convinced that as the number of components increases, chances of failure go up, so we better build our storage system to guard against failure. So what would we do? Okay, we would basically implement some form of redundancy in the system. Okay. Simplest form of redundancy, what is it? Replication. Make a copy, right? So you essentially have, I think this, I'm going to redo this picture, hopefully with a better color. Let's use white. Okay, you have a disk array with 4 disks. Okay. If you want to do what is simple replication, it's called mirroring. You take the left 2 disks, you stripe across those. Whatever data is stored on these 2 disks is replicated on these 2 disks. So block by block. Every block that is stored here is a copy of that block stored there. Okay. So now if one disk fails, it actually has a full mirror within the system automatically. So you are going to transparently just start fetching data from that disk. No different from what you did in your lab, where if one component failed, all the requests started going to the other replica. Okay. Yes, question?
Is it possible to instead replicate your stripes across the 4 disks so you still can access all 4 at once?
Yes, so we'll get to better schemes in just one moment. This is the simplest form of redundancy, which is straight replication, right? So what are some advantages and disadvantages of this? Disadvantage, clearly your storage costs have doubled. Okay, you buy 10 disks, you are essentially getting capacity of only 5 disks. The other 5 disks are simply keeping a copy of your data. Okay? Or put another way, if you want to buy enough storage for X terabytes, you have to spend money to buy 2x terabytes. Okay? So you just doubled your cost. Okay? Having said that, it's a very simple scheme. Okay? So there's always a disk that is backing up every single disk and so on. Okay, but it includes as a 100% overhead. This is called mirroring, or it's also called it's called RAID 1, level 1. There are different forms of redundancy, and they have numbered as it. RAID 0 essentially is plain striping, no redundancy. You're just doing plain striping. Okay, so that's called RAID 0. This is RAID 1. Okay, so I think there's a picture here which is shown there. You will see that every disk, the black disk has a copy, the green disk has a copy, and so on. So essentially 100% capacity overhead. Okay. Now the things to keep in mind, every write has to be duplicated because you have to keep a copy. If you make a write to a file, you take a file and save it, that's a write. That write has to be sent to this group and this group if you stripe it. Okay. So every write is 2 internal writes. Okay. Every read, you can go to the lesser of the 2 loaded disks and read it if there are some ongoing operations. So that's something you want to keep in mind. That's again very similar to your lab, where if you actually write to a catalog or a order server, you have to send the write to both. But read you can actually send to the least loaded one. Exactly the same thing happening here. Okay. So now let's see if we can do better than this, okay, in terms of redundancy but less storage space. So I'm going to actually show you how you can do better. Okay, and this requires you to understand some properties of redundancy and error correcting codes, and I'm going to tell you a very simple property which we are going to use. Okay, and I assume all of you know what XOR operation is, correct? So if you look at how XOR works, okay, if you have two bits A and B and you do A XOR B, that gives you a third bit C. Okay, that let's say A XOR B, the answer is C. If you actually look at your XOR table, you will see that the following property is true. If A XOR B gives you C, then if you do C XOR A, it should give you back B, or if you do C XOR B, it should give you back A. A simple property of XOR operation. You can just look at your XOR table and see that that is actually true. Yeah, because if you have 0 and 1, you do XOR, you get 1. Right? And then if you take 1 and 1 XOR, you get back 0, or if you take the 1 and 0, you get back 1. Is that clear or not? Okay, so I can write it out if it's not clear. Okay, so 0 XOR 0 is 0. Okay, so of course, if you take this answer and XOR with either of these, you're going to get back 0. Okay, 1 XOR 1. Okay. So now if you take either of these two and XOR, you get back 1. Okay. Now you do 0 XOR 1, that's 1. So if you take the answer 1 and XOR it with this left bit, you got back the other one. If you take 1 and you XOR 0, you got back 1. Okay. So this actually works not just for 2, but any arbitrary number of bits, where you can essentially say B1 XOR B2 XOR B3 and so on until XOR Bn. If that's an answer P, you can, if you drop any of these and put P there, you will actually get back that answer because of this is transitive. Okay. Now that seemed to be a digression, but I'll now explain why this is important for us. Okay. Yes.
So you can use like two pieces of data, you can take the XOR of them and store the results. And if one piece of data, like the disk fails, then you can use the error
Yes.
code and another piece of data to calculate what's the
That's exactly right. What you just said is exactly what RAID will do. For simplicity, let's assume that there are only 3 disks now. Okay, so let me redraw this disk. Okay, so now you are storing block 1 of the file here, block 2 of the file here, okay, while you are striping. So what you will do is you will do XOR these blocks and you will get a third block P here. Okay. So now if this disk goes down, you essentially now taken that block and this block, you XOR them, you got back that data that was on that disk. Okay. And because this actually works for n disks, not just 3, you could have many other disks here. So what you will do is essentially, that's what is shown here. You are going to have D0, D1, D2. These are 4 blocks of the file you striped. You XOR them, you got a block which we are going to call a parity block. Okay, that's the redundant information we store. If any of this disk goes down, so let's say this disk goes down, you try to read D1. To read D1, you have to now read D0, D2, D3, and P, XOR them, and you reconstruct D1 on the fly, as if the data has never disappeared from you. Okay? This is called error correcting code. Okay? This is called parity information. You're using property of XOR operation to do this. But the good part now is your overhead has reduced to 1 over n instead of 100%. You don't need an extra disk for every disk. You need one extra disk for a group of k disks that you want to protect. Okay, so this is our protection information. These are all the disks that actually store data. This is storing a redundant information. If any of them go down, you basically now still can reconstruct what was stored on that disk using the parity information. Yes. What if 2 of them go down? Yes. So this error correcting scheme tolerates 1 failure. Okay, it's 1 fault tolerant. If you want 2 fault tolerant, there are more complex error correcting schemes. So you can essentially have error correcting code that are designed to tolerate k simultaneous failure. The most RAID systems will actually do just this. So they can tolerate one disk failure at a time. Of course, if you lose more than one disk, you are out of luck. Go to backups and get it. Okay, so that's what it will do. Yes, question?
How do you check to determine that there aren't bit flips somewhere that just stray?
Okay, the question is how can you decide on bit flips and so on. So that is not something you will do here. This is only designed to tolerate disk failures. It's not designed to tolerate disk corruption of any sort. That's a different problem. That's an important problem, but that's not actually addressed by this scheme. This is simply saying if you have lots of disks, some disks are going to fail. What do we do? Keep some redundant information. This is a better approach than just plain mirroring. Okay. So your question, yes.
Is there any optimal K here?
Okay, is there an optimal K? So the K is basically what is called the size of the parity group. This is called a parity group, meaning that there are K disk blocks and one parity block. Together they form one parity group. Okay, the parity block is protecting all the other blocks of that group. So if any one of those blocks disappears, you can reconstruct. What's the optimal size of K? That actually is going to depend on very interesting things. So as was rightly pointed out, if you have a 100 disk system, okay, if your parity group size is 100, which means there are 99 blocks protected by one block, the chances of two disks failing are actually not small. So what you can do is you can construct smaller parity groups. You can construct groups of 4 or 5 at a time and take your 100 disk array and have smaller parity groups. Within each parity group, you can tolerate one failure. If you have two concurrent failures within that parity group, you are out of luck. But if you have two concurrent failures across two independent set of disks, which belong to two different parity groups, no problem. Right? So first 5 disks are part of this group, next 5 another group. So you can have any one of these disks fail or any one of those disks fail. So you can decide what the right answer is. Okay? Yes?
Do disks actually fail independently? I think there is some results showing that like a manufacturer batch affects sometimes a batch has a very high failure.
Yes. So that's a good question. Right? That's all practical stuff as to disks. Do they fail independently? There may be a defect in a manufacturer block that might cause them correlated failure. Worse, there may be some power surge that causes all the motor of 4 disks to burn out at the same time. This actually will not necessarily fail independently. Okay? That's an assumption that we make. Okay? Now, if you don't want to deal with correlated failure, you got to have more sophisticated error correcting code. That's a K out of n disks fail, I can still reconstruct. That's not a problem. It's just that the extra cost, extra storage costs of redundant information just keeps going up. The complexity of the scheme goes up. That's all. Okay, so this simple RAID arrays will just do this, but you can have more complex schemes as well. Okay? Now, this is called RAID level 3. We skipped actually, RAID level 4. We skipped RAID levels 2 and 3. 2 is just doing bit level parity, where you do this for each bit you store here. Typically, most disks will do block level parity. They will essentially take this block, and XOR the bits of that block and get a new block. Okay, so this is called RAID level 4. Okay. Now, you might say, what are some pros and cons here? So here are some issues. Every time you write to a file, let's say you update a block of the file. Okay, that is going to require you to reconstruct the parity because the parity has to be updated. You have to redo the XOR operation. Okay. So every write triggers what is called a read, modify, write cycle. Okay. So to write a single block, if I update, let's say, one character of my file, okay, and hit save, and it only changed that one character here. Okay. What you have to do is to modify this. You have to essentially now read D0, D1, D3. Okay. Then you basically take the new version of D2, XOR it, and then save D2 and the parity. So you're essentially reading the stripe group minus the parity. Okay. You are updating the parity and then writing blocks. So one write is going to trigger K plus 1 IO operations. Because every time you write, you got to update the parity group. The only way you're going to update the parity group is you have to have all the blocks to redo the XOR operation. So you got to read them from disks first. Then you basically update and you write. So it's always better to actually not have small writes, but have large writes. So if you write, let's say, 4 kilobytes of data where each block has 1 kilobyte, then you don't need to read the whole information. You can just, because each of these blocks is getting overwritten, you just compute the parity and write them out. Okay? So large writes are always more efficient in RAID than small writes. Small writes are going to trigger a read modify write cycle, which means a lot of IO operation just to do one write. Okay, in a standard disk, one write is actually one write on disk. In RAID, one write could be lots of IOs on disk. Okay, and of course, if disks fail, then you are basically run in what is called degraded mode, where you are going to have to read, for every read you are going to have to read the entire stripe group. So k minus 1 reads for every actual read. Okay. So all of these are overheads. Okay. Furthermore, okay, in addition to this, another problem is that this disk, the green disk, the load on that disk is actually going to be the sum of the write loads on all the other disks. Okay. With every write to this disk will of course update the parity block. Every write to some other block on this disk will also update the parity block. Okay. So if I basically write D0 and D5, which is the red blocks here, they also trigger 2 writes here. So the write on that disk, the load on that disk is actually going to be the sum of the load on the other disk. So that will be the most heavily loaded disk in the system. Is that clear? Okay, so you obviously don't want that, because you saturate the parity disk, your entire system will slow down, because you cannot run faster than the size, than the rate of your parity disk. Okay, so what could you do? This is called RAID 4. Okay, so we'll now talk about RAID 5. So what would we do to solve this parity disk is overloaded problem? You answer. Yes. So is there any reason? So you should ask, why is there a reason to store all the parity blocks here? For every stripe group, let's keep the parity block on a different disk. Okay, so this is called distributed parity, which is essentially what RAID 5 is going to give us. Okay, so first of all, that was just the operation saying that you do XOR, you get the parity and you store, etc. So here parity disk becomes the bottleneck. So this is RAID 5. Okay, so you'll see in the first stripe group, the parity block is stored on this disk. The second parity group, this parity block. So the parity block is now scattered everywhere. Okay? So that means that every operation, write operation, which also triggers an update of the parity, that's now getting distributed across all the disks in the system. Okay, much better than RAID 4. So this is called RAID 5, which is distributed parity. Okay. So we started with RAID 0, which is just striping, no redundancy. RAID 1, simple mirroring. For every block, keep an extra block. Okay. RAID 2 is skipped. RAID 3, 4, and 5 just use parity. Okay. RAID 3 is bit level parity. RAID 4 is block level parity. RAID 5 is block level parity, but no dedicated parity. It is just scatter the parity blocks everywhere. Okay. So this is called RAID. We'll come back to RAID in just a moment when we go back to xFS. Any questions on this? Okay, this is what most large storage servers will actually have multiple disks. They'll construct a RAID array. So you will essentially see a giant logical disk, that's the union of the storage space, and all of this disk internally there will be parity. All of this is actually done on hardware. So you will actually implement a RAID controller in hardware that's doing this XOR operation in hardware. You could also do that in software. You can implement a software RAID, but that means that you have to read all the blocks, use the CPU to construct XOR. That slows everything down. If you have a hardware to do this, everything is much faster. Okay, yes, question.
Isn't because you have to write one whole block, if you write with this, isn't bit level parity indirectly also block level parity? So how does it differ technically?
Okay, in bit level parity, you will store the bit 1 of the file here, bit 2, bit 3, bit 4. And then sort of stripe bits, as opposed to block level parity, the first k bits are stored. If the block size is k, you store the first k here, second k here, third k here, and so on. Okay? So what that means in bit level parity is if you read 5 bytes of a file, okay, if those 5 bytes belong to the same block, in block level parity you will only get D20. In bit level parity, you are essentially going to read 5 bytes, you might actually read all blocks of the parity.
Oh, they are bytes.
Yeah, because they are just striping bits, not striping blocks. Okay, so that will needlessly increase the load, because you are still better off reading blocks because of the seek times and things of that sort. Okay, that's a good question. Any other questions here? Okay, So that's RAID 5. There are all sorts of animations which I'll skip. Okay, now we'll come back to RAID in just 1 minute, because in xFS we are actually not going to use hardware RAID, we are going to use software RAID. But there's one more concept I want to talk about before we come back to xFS, which is xFS uses what is called log structured organization, or LFS, a log structured file system. Okay. The LFS was a separate concept that was designed as a separate file system, and xFS just uses it. So it was not a distributed file system concept, it was just a concept that was designed for standard file systems. But it's good to actually spend a minute to understand what log structured organization is and why it made sense. Okay. So for that, I'm going to simply draw another picture. Okay. So let's take, for a moment, forget about distributed file system. Let's take a single disk file system, one disk. Okay. Let's assume that applications are accessing this and sending read and write requests to the disk. Okay. And for sake of simplicity, let's assume that the number of reads and writes is balanced. There are half the I/O operations are reads and half the I/O operations are writes. Okay. So 50% read, 50% write. Okay. That's the traffic that is coming into the file system. Okay. Now, most file systems or operating system, for performance reasons, are going to put a cache, okay, where you are going to put an in-memory cache, because disks are slow. All I/O operations are slow. This is something you should know. Okay. Disk access times takes milliseconds. Okay. So you are going to essentially stick a memory cache. Okay. So this is disk. Okay. Here is a memory cache. Okay. So you are going to put a memory cache, and frequently accessed files, blocks are going to be kept in the memory cache. Okay. So now let's assume the same I/O operation now first come, and they are going to first look in the memory cache. If it's a cache hit, you're done. You're going to serve it from the cache. If your cache miss, then those cache misses are going to actually go to the disk. All writes will always go to the disk. Okay. Writes basically just go to the disk. Reads are going to get filtered out at the cache for cache hits, and only the cache misses are going to go into the disk. Okay. So now if you ask the following question, if initial traffic is 50% reads and 50% writes, okay, what is the traffic going to look like that actually gets filtered from the cache and goes to the disk? Okay. So incoming traffic is half and half, but you put a cache, so some requests are getting served from the cache. What is the traffic that the disk is going to see? Does the question make sense? No, question doesn't make sense. So let me repeat the question. Okay. So the application requests are half reads and half writes. Okay. And because you have put a memory cache for the disk, some of the reads are now going to get, some or a lot of the reads might get service from the cache, because they tend to be cache hits because of locality of reference. All writes always have to go through the cache to the disk, because you have to write the data to the disk eventually. Okay. So the question is, if the traffic that is coming into the OS was 50% reads and 50% writes, after the cache has served some of those requests using cache hits, what is the rest of the traffic here going to look like? What is the disk going to see? Okay. More writes than reads, right? Because every write is going to be seen here by the disk. Every single write comes here. Okay. Only some fraction of the reads are going to be seen. Let's say the cache is extremely effective. You get 99% cache hit rate. Okay. So that means only 1% of the reads that are coming in the system are actually going to the disk. But all 100% of the writes are going to go to the disk. Okay. So you basically saw half and half, but what the disk is actually seeing, if you put a big cache there, is mostly write traffic. Okay. This is actually what most operating systems do, and as a result, because caching is indeed effective, the actual I/O operation seen by the disk, barring occasional cache misses, is predominantly writes. So disk traffic for most file system ends up being predominantly writes, with some reads that are just cache misses. Okay, that's an observation. We haven't done anything with that observation yet. Is this clear? And that's true of caching too. You should actually think about your lab. If you have, once you put a cache, what is your catalog server seeing? It's mostly seeing only bytes. All the reads are actually going through the cache because the cache is filtering all the reads. So your database only seeing writes, and occasionally when there's an update, you will see a cache miss, but then again, it's only see writes. Okay? Same thing is actually happening here. So now you can ask the following question. If my file system sees mostly write traffic and occasional read traffic, how should I rethink my file system to optimize it for write traffic? Okay? Because if the writes and reads were equal, you should say, I don't actually optimize for reads or write. They are equally likely, so I just design the way I always design. But now we are going to say most disks are only going to see lots of, not only, mostly see write traffic. So shouldn't we optimize the file system performance for writes as opposed to reads? Okay. So then the question is, what is the best way to actually store files on disk so that it is optimized for the writes that are coming in? Okay, so this was actually the design behind a log structured file system. They made this observation. They said disks are only seeing writes. Why design the file system the way they used to be designed? Let's rethink how to redesign it so that it's optimized for writes. Okay? So now you can think about how am I going to serve a write only traffic. So typically when a file system gets a write request, it's going to allocate some disk block that is free and say that data gets returned to that block. And all the data gets randomly written wherever there is empty space. Okay? So one block might get written here because that block was empty. The next write might get written there because that block was empty. You just find a disk block that is free and just write the disk block, and it doesn't matter where the disk blocks are. So long as your disk block free, you are going to write it there. Okay? Now we say it's mostly writes. So what will we do that is actually useful for us to optimize write performance? Okay. So you should say, what does it mean to optimize write performance, okay, or even I/O performance for that matter. Okay, now this is true. Okay, I should mention this is true for older magnetic disks. It's no longer true for solid state disks. In an old magnetic disk, the way you actually service an I/O request is because you think of a CD as an example. Okay, the CD is spinning. There's a disk head. Okay. Now, if you want to read a random block I, you have to actually move that disk head to where that block is. So that's called the seek time. So you are actually moving the disk head back and forth so that you actually go to where the data is and then read that data. Okay? And if blocks are randomly stored, every block is going to incur a seek operation because you have to first move your disk head to that location on the CD where it's spinning and then read that data. Okay? So every I/O operation is going to at least have a seek operation. Okay? So to optimize I/O performance, we got to reduce our seek overhead. Okay, because seek is wasted time. You are not actually reading or writing. You are simply moving the disk head to go where you need to go. Only then you read or write data. Okay. So how would we reduce seek performance or reduce seek overhead? Yes.
So if you optimize for writing, for writes, you can possibly just fix the write head and write sequentially.
Right. So that's exactly. So the best case that you can get in a disk is no seek overhead at all. The way you are not going to get seek overhead is if I write disk one block at a location I, if the next block gets written to location I plus 1, there is no seek. You just keep writing. Right? So you don't have to, otherwise you are going to write one block, go somewhere else, write block, next block, move somewhere else. So you're going back and forth. If you just start writing in a log, append only log, you just keep writing sequentially. This works beautifully if the most traffic is only writes because you keep writing and you just write as a log. Okay, if you had lots of reads and writes, for reads you just have to go back to wherever the data is, so there will be a seek. But if there are very few seeks, very few reads, there is no reason to go somewhere else to read. You just keep writing sequentially. That was the entire design insight for a log structured file system. Log essentially is like an append only file. It says all the data is coming as writes. So I'm just going to take this write right here. Next write goes there. Next write goes. So I basically keep writing sequentially. And that's going to minimize my seek overhead. I'm going to get very high write throughput than if I had random IOs. Okay? So you can, in magnetic disk, you can now get high throughput by minimizing seek performance. That's the insight. None of this matters when you have SSDs. SSDs have no moving parts. You can go to any location on disk and read it at the same way because there's nothing to move. It's like a memory. right? You can just go, it's like an array, you can go and access ith element of the array at the same overhead as any element j. So log structured organization doesn't buy you anything in a SSD, but in magnetic disk it buys you a lot. Okay? So the whole point of a log structured organization is write the data as a sequential log. Okay? And so furthermore, what that means is if I wrote a file here and then I update that file, okay, in a normal file system I would go back to that block and update it there. In a log structured file system, if the block gets updated, I am going to write the new block here and just mark this block as garbage, okay, which will later be garbage collected. Right? So if you repeatedly write to a file, you essentially keep writing to the end of the log. Okay? And then you basically say that, so this is the new copy of that block, so that block should be deleted and so on and so forth. Okay? So one of the disadvantage of log structured file system, as you can imagine, is after you have written many files and rewritten files, resaved that, you will essentially have lots of holes appearing because there's lots of invalid data because the newest data was written at the end of the. So you have to do garbage collection. Just as you do Java garbage collection, you basically have got to go and do recompaction because all these holes that are popped up in between are like fragmentation. You will go and recompact all your log and remove the hole. So you shrink the log and keep all the space with that. Okay, so every once in a while you are going to run garbage collect, which typically file systems don't have notion of garbage collection. Okay, so here you have to do this to defragment your log and essentially recreate storage space. Otherwise, you will have to write in the holes, which means that you will see seek overheads again. Okay? So that's a disadvantage of log structured file system. Okay? But let's not worry about that disadvantage. The good part is it gives you very high write throughput. Okay? So now we are going to, any questions on this? Yes.
How do you keep track on where the current version of the file is? But I think you have to have metadata that you also have to
Yes, that's a good question. So the question is, how do you know where the data of the file is, right? So typically you will have an inode. That inode said the block was pointing here. You updated block 1, you have to update the inode, say now it's at the end of the log, okay, and then so on and so forth. But then you have to write that inode too, right? If you write the inode to the super block, then you got to go seek back to the super block and write. Okay? So in log structured organization, you can actually also write inode blocks as a log and so on to optimize that. But then you got to keep track of where the inodes are stored as well. So it makes metadata management a bit more complicated, but you can still do it. There's a very nice paper that was written on this which explains all of that. But you are absolutely right. Every time you update the file, you got to update the inode. In a normal file system, inodes are stored in a special location on reserved location on disk. Here, if you do that, I got to go back from the end of the log to that special location. That's a seek and keep coming back. So you want to actually write everything in a log, including the data and the metadata. So it increases the complexity. Now metadata is scattered across disk, not stored in a reserved location. So you got to find the metadata before you can find the data of that file. So it complicates a few things. Okay. Any other questions here? Okay. So we learned 3 concepts. Okay. Striping, RAID, and log structured file system. Okay. xFS puts all of them together. Okay. But it does one more thing, which is it takes the notion of striping and RAID and makes it a network striping or network RAID. Okay. So what that means essentially is, so now let's assume that there are machines. Because it is serverless, we are not going to call them clients or servers. Let's just assume there are n machines. Okay? Every file is now going to be striped across machines, not across disks in a single machine, but across machines in the system. So we'll take a file, chop it up into pieces, store chunk 1 on machine 1 or disk on machine 1. Second chunk goes to the disk on machine 2. Third chunk goes to the disk on machine 3. Then maybe you compute a parity and store it on a 4th machine and so on. So this is called network striping. Okay? You're striping blocks of the file across machines in the network rather than across 4 disks that are plugged into the same machine. That's regular striping. Okay, so it uses this notion of network striping. In doing so, what it has done is taken the storage space on all the clients in the system, all the machines, and made it look like one gigantic logical disk. because you can use all the storage space everywhere in your system rather than just on one machine. Okay. So, it is going to use network striping and it is going to use software RAID, because you cannot possibly take 4 blocks and use some special hardware, because these blocks are now on different machine. So, all of the XOR etc. has to happen in software and write things out. In a normal RAID, you will have a special card that will do that for you. Okay, but that's okay. Okay, so, you are essentially now going to do network striping. You are going to use network RAID. Okay, RAID is now actually distributed across machine. Okay. Furthermore, you are going to use log structured organization. Okay, you are essentially going to stripe a log file, not individual files. You are going to just keep striping, but you are going to write the log out. Okay. So, within each disk, you are going to write sequentially, but the log is actually striped. So, all the write operations are written like logs on individual disks on individual machines. So, you get the benefit of log structured organization. You get the benefit of using multiple machines. So, parallelism is still there, and you are going to now use RAID to essentially say if one machine dies or one disk on the machine dies, I can still keep my data intact. Right. So, you put all of that together, you can start seeing what xFS is, a fairly complex file system. Okay, and then all the like exactly what was pointed out earlier. I may have a picture somewhere. So, you will see that there are all sorts of, there are storage servers where you are striping, there are metadata managers that are not stored there, because metadata is also striped, it is also written in a log. So, to figure out where a file is stored, you got to find the inode, to figure out which machines it's stored on. So, a lot of additional bookkeeping has to be done to implement all of this. But if you do that, you essentially get the benefits of 3 different innovations in storage system. Okay, you get striping, which gives you parallelism, you get RAID, which gives you fault tolerance, and you get log structured organization, which gives you high write throughput. Okay, so this file system puts all of that together into one single file system, and in doing so, it also essentially gives us the, okay, actually that's the picture I wanted to show is right here. So these disks are now individual machines. So you essentially have a log, okay, that you're writing them out. You basically chop the log into blocks, you compute a parity blocks, then you store block 1 on machine 1. This is a disk on machine 1. So you're essentially doing network striping, network RAID. Okay. Any questions here? Okay, so let me spend the remaining 5 or so minutes we have talking very quickly about 2 other file systems which you may have encountered. One is called HDFS or the Hadoop file system. The other is called GFS or Google file system. Okay. So these are designed for somewhat different use cases than xFS and so on, which are designed for general purpose file system use. Okay, HDFS is essentially used for processing very large data sets. Okay, because it's typically used in Hadoop, which is using MapReduce and is doing large scale parallel data processing. Okay. So this file system essentially has the following goals. First of all, large data sets, lots of disks are going to be used to store it, so you need fault tolerance. Okay. Essentially, you are going to do batch processing rather than interactive, because most of this data is used for batch processing. So you have to design this for batch use, not for interactive use, where you open a file in an editor, you edit it, save it. That's more interactive use. So you will need lots of data in a batch, process it. Okay, very large data sets, and typically these data sets are going to see what are called worm workloads, which is write once, read many. Okay, if you get 100 gigabyte data set, let's say vision data set to do some vision processing, the images are not going to get updated. You might add new images, but once you store it, they are going to stay as is. But you might read that many times every time you process that data set. Okay? So many scientific data sets are actually write once, read many. You construct the data, you produce it, but you don't change it once you produced it. You might append it, expand your data set and so on. So how would you essentially optimize your files when you only write it once, you never actually update the file, but you read it many times. Okay? And then you might have to decide based on where the computation is, how you are going to store your data and so on. Okay? So many different things are done in HDFS, not all mentioned here. First is the block size is very large. Typical file system use 4 kilobyte blocks. In HDFS, you might use several megabyte size blocks, 64 megabytes. Each block is 64 megabytes in size. Okay, that means if your file is typically assumed to be much larger than a block size. Okay, so if you create a 1 kilobyte block and store it on HDFS, you're still going to take a 64 megabyte chunk and only use 1 kilobyte, and the rest of it is wasted. Okay? So it's not designed for small files, clearly, it's designed for large data. So because your large chunks, you read it, it's one seek, and then you read a large amount of data together into memory. Okay? So you're optimizing seek overhead again. Okay? So large block sizes, that's one. Second thing they do is they don't bother about RAID. Okay? So is a RAID too complicated? Instead, we are simply going to replicate every file 3 times. Okay? And the assumption is disks are cheap, RAID is expensive. Let's make 3 copies and store them on 3 random servers. Okay? So replication factor of 3. Even if 2 disks, 2 machines fail, I still have a third copy. And by and large works well. You can tolerate 2 independent failures and still your data is intact. So every file that you create will be partitioned into chunk, make 3 copies of the chunk, put them on 3 random servers. Okay, so if anything fails, you still have 2 other copies. If 2 copies fail, you still have a third copy. So no use of RAID in this case. Okay, very simple replication. Default factor is 3. You can configure it to whatever you want. You can say, I don't want to replicate. Then if something fails, you're out of luck. But the default is 3. So large block size, okay, replication factor of 3. And the most important difference is you will see that there are 2 types of server nodes. There's metadata servers and data server. So because the files are large, you have separate machines whose entire job is just to keep track of where the data is stored. Okay? These are called metadata nodes. Very large scale file systems actually have metadata nodes, and then they keep track of where the files are stored on data nodes. Okay, so when you access a file, first you go to the metadata node that has the index. You look at the index and it will say block 1 or chunk 1 is on these 3 nodes. Block 2 is on those 3 nodes, and so on. Then you go to one of the nodes and start reading them. Okay? So that's essentially just a 2-minute introduction to HDFS. And the Google file system is no different. Okay? There's a paper on the Google file system which has very similar goals. Okay? Large data sets want to basically get high throughput. So you essentially are going to partition your files chunks, store the chunks on multiple machines. Again, they independently also came up with let's replicate each chunk on 3 different machines, because that's basically the way we are going to deal with failure. Okay, so you will see a picture here. So this is, again, there's a separation of data and metadata. This is your metadata node. This is where the index is stored. So you will see that there's a file sector tree. For every file, there's an index which tells me which of these machines actually stores these files. Okay, so you will say chunk 0 is on this machine, and it's replicated on those other machines and so on. And as far as the actual chunks are concerned, it doesn't even bother creating a new file system. It simply stores them on a standard Linux file system. So if you have so GFS is essentially a layer on top of a standard Linux file system, except that you will see that that file system just stores some large blobs which you can't make any sense out of, because they are chunks of some larger file that is tracked by GFS. Okay? But you will keep large block sizes, so and you will read them all at once to reduce seek overhead and so on and so forth. Okay, yes, question.
How does S3 differs from GFS?
Okay, that's a good question. How does S3 differ from GFS? Our last thing is actually S3 here. So, so the last storage system in the 1 minute I have is to think about object storage system as opposed to file storage system. Okay? There are many storage systems that are designed to store what are called objects, not files. Okay? Object is just a blob of data which has a key, and you specify the key and you get a handle. And the handle will give you back the object. Okay? So in a file system, you have a file hierarchy. You give file system names. You have a directory structure. You can group files into folders, and subdirectories can be created and so on. Okay? In an object storage system, there is no hierarchy. Everything is flat. Every object you store, an object could be a file from your perspective. Every object that you store is going to give you a key. Think of a hash on the object. Okay? That's what you're going to use to retrieve the object. There's no file names. Okay? So it's a key, it's a very large key value store. You present a key and you get back an object that maps to the key. So it's a very, think of it as a gigantic hash table where you have a key for every object. Objects could be of arbitrary size. They're going to be stored on your storage system. Right? That's one. The second is S3, like many other HDFS and so on, also doesn't use RAID. It actually replicates every object. In fact, it replicates them not across machines, but across data centers. So even if an entire region data center went down, a data center could be thousands of machines. You actually have a copy in another continent or another country somewhere. Right? So it does geographic replication. Okay, it's called geodistribution, right? Which neither HDFS nor GFS do. So you can actually tolerate very large scale failures. If the power goes out in an entire data center, you still have copies in some other machines which may be sitting on some other country and so on. Okay? So the main difference is, okay, the last thing is it is using HTTP to access files. Right? As you know, you have get and put requests to actually do S3 accesses as opposed to standard file system operation. Okay? So HTTP access, okay, use of large blocks or objects which are essentially keys. They don't have a naming scheme like you have in a file system, and you have geodistribution. You replicate like you do in case of GFS, you replicate 3 times at a minimum, but you put them in different data centers altogether. Okay. So these are called object storage systems as opposed to file systems, because they don't actually give you files, abstractions, and so on. Yes, question.
How do you metadata? Because there are so many objects.
Okay. How do you keep track of metadata? So there are 2 things. One is, how does the user keep track of their metadata? Users can actually give human readable names to their objects, or what are called buckets. So you basically have bucket names and you access them through a URL. So you can give human readable names. Internally it gets mapped into a key. Okay, and then internally there's an index that is going to allow you to keep track of this object, where is it stored, and so on and so forth. Okay, so that's way to keep in mind.
How the server keeps track of it.
Yes. So how does the server? It has to keep an index internal, just as GFS and HDFS have metadata servers. So metadata servers are gigantic tables that say this object stored has these chunks that are stored on these machines and so on. Right? So that's not mentioned here, but you will have metadata servers doing exactly that. Okay. So we are over time. So I'm going to stop it here. We are done with file systems. We'll talk about middleware next time. Yes.